Hello, everyone, to all the audience for the second day of the MoroccoAI Conference 2024. I have the pleasure to start this second day, and I hope that you have enjoyed the first day with the amazing talks, the amazing distinguished speakers we had yesterday. And we continue that today. We do have a long list again of very interesting speakers, very distinguished keynotes. And we will start. I have the pleasure actually to start today with Dr. Salem Lahlou. So Dr. Salem Lahlou is an assistant professor of machine learning at MBZUAI in the UAE. His current research is focused on AI for science tools, including but not limited to uncertainty quantification, interactive learning, and language model reasoning. So recently he has been involved in developing GFlowNets, a new class of generative models of compositional objects that find directly applications in speeding up the scientific discovery process, both from a theoretical side and through an open source library. More generally, he is interested in understanding the mechanisms behind intelligence, be it human or artificial. He studied at École Polytechnique in Paris and received his PhD from Mila under the supervision of Yoshua Benjou, of course, our national pride, and who was the honorary speaker of our very first conference 2021. So we are saying hi to Prof. Yoshua Benjou if he's watching us right now. And Salem was also previously held positions at Booking.com, IBM Research, Google Research, TII. So it's a very, very impressive CV and career for a young researcher. We are very pleased to have you with us, Dr. Salem Lahlou. And yeah, the floor is yours.
Thank you for the great introduction, Sylvain. Let me share my screen and start my presentation. So first of all, thank you for waking up so early if you're in Morocco to listen to my talk. I believe everyone sees my screen, and today I will be talking about how machine learning is used and can be used for experimental science. And maybe let me start by reminding you of this news that you are probably all aware of. So in October 2024, we witnessed something novel. So it was the first Nobel Prize that was awarded to artificial intelligence researchers. And this wasn't just any achievement, it was AI solving a fundamental problem in biology that scientists had struggled with for decades, which is the ability to predict protein structures. And this has massive impact for drug discovery, for understanding diseases. And I guess this Nobel Prize signals that AI isn't just a tool, but it's actually reshaping how we do science. A quiet revolution is brewing in labs around the world where scientists' use of AI is growing exponentially. Society will soon start to feel these benefits more directly, with drugs and materials designed with the help of AI currently making their way through development. And what started with protein folding is rapidly expanding across all scientific domains. And I'm going to provide many examples during my talk and then delve into some specific details of algorithms, of works that I've been involved in. Let me show you maybe how seriously this revolution is being taken. So major institutions like the US Department of Energy, the European Commission, they're aligned in their vision. In 2024, they recognized AI for science as an opportunity, and they're actively advocating for public strategies. And I guess this alignment, it shows how significant this moment is because different nations are interested in that and really pushing the whole world to embrace this opportunity. So before diving into examples and details, I want to show you specifically why you should care about this revolution. So let me start with this Sustainable Development Goal report by the United Nations in 2023. And it gives a quite pessimistic view of our global challenges, from climate change to biodiversity loss, from energy security to food systems. And the reality is that this report and many other reports, they mentioned that there is a growing imperative behind the embrace of using AI for science, because progress towards these sustainable goals of 2030, which capture biggest challenges in health, environment, and beyond, this progress is stalling. So that's why we need things that can accelerate this progress. And these problems that we face, they require scientific breakthroughs, and they need them fast. So, and perhaps like one last point, this is the last point I mentioned here. This is independent, this is orthogonal to the current economic system. So whether we are in a growth system or a degrowth system, whether we reduce our consumption or not, we still need fundamental scientific advances to address these challenges. So new materials for energy storage, better ways to remove carbon from the atmosphere, more efficient ways to produce food. So these aren't just nice to have innovations, but they're essential for our survival. And this is precisely where AI can make a difference. Let me show you some concrete examples now. This is a diagram that shows electrocatalytic CO2 reduction. I'm not a chemist, but I'll explain in very simple terms. This process shows how using catalysts can transform harmful CO2 into useful products like methanol. And it's basically like recycling CO2 into something more valuable. And the challenge is that we need to discover new catalysts that can do this efficiently, because the ones that we already have aren't good enough. Another important challenge is this diagram that I borrowed from this paper, which shows, again, a pessimist view of how bacteria are becoming more and more resistant to antibiotics. They're becoming resistant faster than we can develop new ones. And yeah, basically every time we develop a new antibiotic, bacteria find ways to resist it more quickly. And therefore, we urgently need to discover new drugs. And yeah, we need to do it faster than before. And AI can help for that. And as a last example of these challenges, if you focus on this diagram above about carbon capture and storage, so even if we reduce emissions, we need to deal with the current carbon dioxide that we've already released. And to do this effectively, we need to discover entirely new materials that can trap and store CO2 for long periods. And these materials, they need properties that we haven't fully figured out yet, and AI could help for that. Before delving into the technical details, I want to take a few minutes to tell you what AI for science really means. So let's take a step back and talk about something bigger. So in 2019, there was this book by Microsoft Research that introduced the concept of fourth paradigm in science. This fourth paradigm means that there is a fundamental shift in how we do science itself. And what I mean by paradigm shift is that when the basic rules of how we do science, they change completely. Maybe a good metaphor for that is, switching from thinking that the Earth is flat to understanding that the Earth is round. This is like a paradigm shift. So it changes everything about how we understand the world. And this idea of paradigm shift wasn't new. So back in the 60s, so Thomas Kuhn, it changed our understanding of how science itself progresses. So he showed us something which I found fascinating, which is science doesn't just grow by gradually piling up new facts and theories, but sometimes it takes some dramatic leaps. There are some discontinuities in the scientific process. So this is what he called scientific revolutions. And that's exactly what's happening now with AI in science. So we're not just getting better at doing science the old way, we're actually completely changing how science is done. So here I'm mentioning scientific progress. I haven't completely defined what scientific progress is. Perhaps we'll get back to it later. But first, let me show you what these four parts. So this is the four paradigms. So let me show you what the three other paradigms are. So perhaps the simplest one, I guess, the oldest one since humanity existed, we have been using empirical science or empirical evidence. So basically simple observations, like if you see smoke, it makes sense to believe that something is burning. So this is pure observation and documentation. Then came the theoretical paradigm where scientists developed mathematical laws to explain these observations. So maybe you can think of Newton's law of motion or thermodynamics. And in the last century, with the advent of computation, we could simulate complex systems and solve equations that were impossible by hand, like how modeling atoms interact in materials. And now we are in this fourth paradigm, where AI and machine learning, more specifically, are transforming how we handle and learn from scientific data sets. But here's what makes this different. So it's not just faster science, but it's something fundamentally different. And now I'm going to show you some concrete examples where machine learning has already revolutionized how we do experimental science. So it's not just the future of how machine learning can help, but already success stories of machine learning being used in science. So this is the picture of a protein that was discovered by AlphaFold a few years ago. And it's not really interesting for the sake of my talk what this protein really does, but what's really amazing is how we found its structure. So protein structure prediction is a very challenging problem in chemistry and biology. And it's about figuring out how exactly a protein falls in 3D shape. Like, a protein, you can represent it by a sequence of amino acids, but in reality, it folds in a very special way. It looks like this figure that you see here in the top. And traditionally, scientists were using experimental techniques like X-ray crystallography or some fancy microscopy to determine these structures. But the reality is that in 60 years of using these expensive and time-consuming methods, the scientists only managed to map about 170,000 protein structures out of 200 million known ones. So that's less than 0.1%. But with this 170,000 protein structures that were discovered before, we could, scientists could create this protein data bank, which is a public repository of these 170K protein structures. And then came AlphaFold, which uses supervised learning to predict new structures. So it was trained on this protein data bank to predict the new structures of new amino acids. So it was able to generalize from those 170K structures to new ones that were not found before. So this AlphaFold basically, some people said that it changed everything because protein folding was a very hard problem. And it's not the only fundamental scientific challenge AI is tackling. I'm going to show you another example where AI is actually changing how math is being done. Perhaps you have seen this in the news the past year. Maybe you could realize that I'm showing you examples of very recent years, maybe to highlight also the fact that things have been advancing at a very fast pace in the past years. So AlphaProof was trained to discover mathematical proofs. And it was trained using reinforcement learning and other techniques on about 1 million math problems. And what you're seeing here is how the machine learning algorithm breaks down mathematical reasoning into steps, like what mathematicians do. And it's not just about solving equations, it's about discovering entirely new mathematical proofs. So this AlphaProof and other similar techniques, they won the silver medal in the International Mathematics Olympiad, like the event that is held once a year and gathers the best high school students in all the world. They got the silver medal with this algorithm. I have some other examples. I don't have slides for that. So maybe in astronomy, AI is changing how we discover new celestial objects by analyzing millions of telescope images to identify maybe new galaxies and exoplanets. In physics, AI is solving complex inverse problems like reconstructing complex quantum states. And these problems were previously either impossible or would have taken decades to solve. So this brings us to the next section of my talk, which is where in the scientific process can AI make this kind of, can AI help? And let's start with the most straightforward use, which is predictions. So here's a typical setup, supervised learning. We feed some input to a system. So the input can be like a molecule structure, and we want to predict some properties or maybe how the input will behave. So this is supervised learning, and I don't need to explain much about it. Where it gets more interesting is that modern machine learning techniques don't just give us predictions, but it tells us how confident they are about those predictions. So this uncertainty awareness is very important in science because we need to know whether we can trust predictions or not before spending months and millions of dollars to synthesize new compounds or to make very fancy experiments. And in fact, later I'll show you some of my own research and with my colleagues on how we can estimate the uncertainty of neural networks, something that's always been challenging. So this leads us to, I guess, the most exciting application, which is combining these uncertainty-aware predictors with our scientific objectives, like specific properties we want or constraints that we need to satisfy. So machine learning can actually guide our decision-making process. So it can suggest which experiments to run next, which molecules to synthesize, or which thing to design. So this is where machine learning becomes more than just a prediction tool. It becomes, I guess, an active partner in scientific discovery. So I'm borrowing this diagram from the DeepMind report I mentioned before. And here is how many researchers break down the opportunities for AI in science. So there are 5 areas. So we have knowledge management, data handling, simulation, modeling complex systems, and finding novel solutions. And I'll walk you through each of these areas in detail, starting with perhaps the most fundamental one, which is how AI is changing the way scientists handle knowledge. So let's focus on this knowledge part. So as scientists, we're drowning in information. There are millions of papers that are published every year, and many noise, a lot of noise in that scientific literature. So innovation requires mastering scientific literature from multiple domains, and LLMs are already helping scientists navigate this flood of information, summarizing papers, and even conducting literature reviews. And I guess maybe the fascinating part is that this might fundamentally change how we write and review scientific papers. Many researchers are asking this question of whether it even makes sense to write the papers the same way that we did 10 years ago or 150 years ago. So maybe it's time for a rethink. But I guess this is important, we're not there yet. As you probably know, LLMs still lack reasoning abilities and they heavily hallucinate, so we cannot trust them fully in this knowledge extraction phase. Here I'm showing you like a diagram from our recent work called PORT, Preference Optimization on Reasoning Traces, where we showed that sure, advanced language models still struggle with scientific reasoning, but we're making progress in this paper by teaching these models to distinguish between valid and invalid chains of thought using techniques like preference optimization, just TPO thing here. Now, I won't go too much into the details here, but there's still a long way to go. This does not solve the problem, and many groups of research around the world are spending many resources to solve this reasoning and hallucination problem of AI. So for now, I guess it's better to think of AI as an assistant rather than a replacement of scientific thinking. So going back to this figure, let's focus on the second key challenge, which is data. And I guess here there's a paradox because AI needs data to help science, but we often lack this high-quality scientific data that is needed to train AI models. And there is something clever that is happening, and that can happen even more, which is we're using AI to help solve this very problem. So for instance, machine learning algorithms can reduce noise in DNA sequencing, maybe like making algorithms more accurate. They can extract meaningful information from sources we couldn't easily use before, maybe like automatically understanding diagrams in some old papers, or like many teachers and professors, they publish their scientific lectures online. So machine learning tools could help extract knowledge from those scientific lecture videos. Also, they can help annotate new data, making it more useful for future research. So the third point is more exciting opportunity on how AI can help us with experiments themselves. So let me show you what I mean. So scientific experiments like in fields like fusion or drug discovery, they can cost millions and take years to do, but we can build accurate simulators of these experiments and then optimize the processes within the simulators and then transfer those insights into the real experiments. This is a subfield of machine learning called transfer learning and domain adaptation. Let me show you some concrete examples. So in this paper, scientists use AI to control nuclear fusion experiments. So as you probably know, nuclear fusion could give us nearly limitless clean energy, but it requires controlling plasma, heated to temperatures hotter than the sun, I guess. And what you're seeing here is how AI learned to control these plasma configurations in a simulation first, then successfully transferred to control in real fusion experiments. So this isn't science fiction, it's actually happening in fusion labs today. And maybe this brings us to an even broader question, which is how can AI help understand complex systems? So machine learning models can spot patterns that humans might miss simply because they can analyze way more data than we could ever do. And they can make predictions across a large range of scientific domains. Again, a few examples at the molecular scale. In this, I won't spend a lot of time here. No need to go to the details, but here AI is predicting how catalysts behave on nanoparticles. Here I have a paper where they use neural networks that predict quantum mechanical energies and forces, which help us understand, the most fundamental level of matter and energy. And if we zoom all the way out to the Earth atmosphere, in atmospheric science, there are many trials and many successful trials like this GraphCast that outperforms traditional weather prediction systems by learning from historical data. So last thing is to understand that prediction itself is not enough. And this is where everything that I've mentioned so far comes together. So AI can help us optimize incredibly complex problems. So whether we're designing new molecules or figuring out the perfect conditions for an experiment, so these challenges in science aren't just about understanding, it's about finding the right solution among many possibilities. And machine learning has the potential to efficiently explore large state spaces. In fact, later I'll show you some of our work on a new approach that's called GFlowNets, which offers a powerful new way to discover solutions in these large spaces. But before we get there, let me show you how machine learning can accomplish these tasks. Maybe the specific techniques that makes all of this possible. How machine learning can help. So if you remember this diagram earlier, I mentioned how important it is for AI to know when it's uncertain before we trust its prediction for scientific decisions. But it turns out when we deploy a machine learning model, there are two types of uncertainty. First, there is the aleatoric uncertainty, which is the inherent randomness in the measurements, like when we repeat an experiment and it gets slightly different result at each time, or perhaps a more fundamental uncertainty type at the quantum level. And then there's the epistemic uncertainty, which is more important here, because it's the uncertainty that is due to the lack of knowledge or due to the lack of data. And traditionally, statisticians or machine learning researchers, they use this Bayes rule to capture these uncertainties. Like we have some data and we have some parameters about our model of the world, and we need to estimate this posterior. But it's actually impossible to compute exactly because of this denominator here that's interactable. So this is where our recent work comes in. So in DEP, direct epistemic uncertainty prediction, we developed a new way to estimate epistemic uncertainty even when we don't have a lot of data. And the idea is very simple. So we use the actual errors that the model makes on a validation set to train a separate predictor that gives epistemic uncertainty. Another important question in science is figuring out what causes what. So what you're seeing here is called causal graphical models, which shows how different variables influence each other for these edges here. And maybe we don't really need to go into the details of these equations, but what they tell us is how to calculate the probability of different causal relationships from data. But the challenge is that when we have many variables, the number of possible causal structures explodes. And again, this is where our work on GFlowNets, which I'll show in 2 or 3 slides, comes in handy. So it offers an efficient way to explore these complex spaces, like the space of graphs. So it's not only a space of physical objects like molecules or materials or whatever, but it can also be used for machine learning itself. It can be used to create graphs. And maybe this brings me to another important question in science, which is how to choose which experiment to run. So with limited time and resources, it's important to know which experiments will give us the most information. And this is a field called Bayesian Optimal Experimental Design, BOED. This equation called that defines the expected information gain, tell us what is the design or the experiment that is needed to be done in order to get the most information, in order to most reduce our uncertainty about the world. And again, this is where our work could help, both the uncertainties provided by DEP or GFlowNets. They can help us make these decisions more reliable and efficient. Lastly, I want to talk about Bayesian optimization before going to GFlowNets. So this is a powerful method, also called sequential model optimization, where the goal is to maximize some black box function. So imagine you're trying to find the best molecule that binds to a particular protein, and each experiment takes days and costs thousands or millions of dollars to run. So this orange curve here, you can think of it as the true binding energy. That, of course, we don't know it. What we can do, however, is to run a few careful experiments. So these dots, this one, this one, this one. And then we can make educated guesses about what the function looks like. So this is the blue curve. This is our best estimate so far. And importantly, estimate our uncertainty. This is the shaded area here. And this uncertainty will tell us what is the next best point to query. And again, this is where DEP shines. Here you can see like a simple example where DEP is able to outperform other established methods like Gaussian process expected improvement. This is just in a simple 1D experiment, but we have other experiments with up to 100-dimensional functions. And this brings me to something that I find more interesting, which is what if instead of just finding one optimal solution, like at the maximum here, we find all good solutions. So this one, this one, this one. So this is exactly what GFlowNets allows us to do. Let me introduce that. So it's a new approach that was created about in 2021 and has since become a hot topic in the machine learning community. So at its core, we're trying to solve this mathematical problem, which is how to sample from a probability distribution when we don't know the partition function Z. So I know this might sound abstract, but stay with me because it has a lot of implications in scientific discovery. So what makes GFlowNets special is, unlike reinforcement learning, which maximizes a reward function, which tries to find the single best solution, GFlowNets can find many good solutions. So in science, we often want diversity in our discoveries, not just one answer. And some concrete examples that I've already mentioned before. So imagine we're looking for new materials with specific properties or trying to discover new drugs. So in drug discovery alone, scientists, they face a huge amount of candidates. It's about 10 to the 60 small molecules. And traditional methods, they get overwhelmed by these massive spaces. And GFlowNets hold the promise of efficiently exploring these spaces while maintaining diversity. I'm going to take 3 to 4 minutes to show you exactly how they work before concluding. So what you're seeing here is called a flow network. So I guess the easiest way to grasp it is to think of it as a map of all possible ways to build something. So we want to build this object S3, S4, S6, S10, etc. Whether that's a molecule, atom by atom, or a graph, edge by edge. So each path through this network, this directed acyclic graph, represents one way to construct our object, because the same object can be constructed different ways. And then we add these flows to these edges, which are positive numbers that are represented by purple dots here. And what these flows are used for is that we want them to be balanced. So at each state, at each intermediate state of our construction process, we want the total flow that comes in to be equal to the total flow that comes out. So just like, I guess, water flowing through a pipe. And another key idea is that we need to define what happens at the end of each path. So when we find the object that we want to construct, let's say finish building a molecule, the flow needs to match exactly how good that molecule is doing at what we want. So this is called the reward. So the magic is when we satisfy these two conditions, the flow matching and the reward matching conditions, and we use the flows as a guide to randomly walk through the network, we'll naturally discover diverse solutions. So with better solutions being discovered more often. So it's a nice way to explore massive space of possibilities. Then comes the question of how to train such flow networks, how to learn these flows. So you know how in linear algebra classes, you might have learned to solve equations of the type x equal b by minimizing functions of this type. Or maybe in supervised learning, where we want to fit a function, we minimize a function of this type. Well, it's the same idea here. We need to turn our flow conditions, our flow matching conditions, into something that we can optimize. So with these conditions, we can just turn them into this loss. And if this loss equals 0, then our conditions are met. So it just makes sense to minimize this loss using gradient descent. So this opened up a whole new field of research. We have since developed multiple ways to train these flow networks, including the detailed balance loss, variational approaches, and even extensions to continuous domains. And each of these advances, they make GFlowNets applicable to different types of scientific problems. And the algorithm is quite simple. First, we can just sample a trajectory through our network. So that means follow the current policy to build something. And then for each step in the trajectory, we update our parameters using gradient descent, just like in standard deep learning. And what's nice is that we can even sample trajectories using different policies than our current one. So this is what I mean by off policy here. This makes training more efficient sometimes. So before concluding, I want to show you some successful applications in the literature. So here in the 2021 paper, there are the authors showed how GFlowNets were able to discover new drug-like molecules that could bind to specific protein targets. So we have this reward model, which is a proxy of the binding energy. And compared to traditional methods like reinforcement learning, so PPO or MCMC, this is this Mars curve, GFlowNets defined more diverse molecules while maintaining high binding energy scores. So I would like to take maybe 2 minutes to conclude now. First, I want to mention that there is an ongoing debate in the scientific community about what AI means for human expertise and creativity. I know many people have asked this question in the chat of the conference already. So some believe that with enough data and computing power, AI will eventually automate all cognitive work, including scientific discovery. Others argue that true scientific breakthroughs require creative leaps that AI simply cannot make. And I guess the truth lies somewhere in between, like everything in life. And there is an even more important discussion that we need to have. So I showed you some great potential of AI in science, and I would have loved to finish on a positive note, but I feel obliged to address something that I feel very important, which is that these powerful tools are already being misused. So from manipulating public opinion through bot networks using LLMs to maybe manufacturing consent through some targeted propaganda. And the stakes can get even higher for AI in science. So if we don't have proper oversight, the same algorithms that could be used for drug discovery, well, they could be used for targeted bioweapons. The same tools that could solve humanity's challenges, they could further concentrate the powers in the hands of a few people. So here's maybe a fundamental question that we must ask. And this is my last slide, which is who decides the direction of progress? Right now, I think it's not hard to argue that market forces and private interests are the ones who largely shape AI development. And scientific advances, they follow profit incentives, not societal needs. And if we want AI to truly serve humanity's needs, we need some kind of democratic oversight and good public policies that steer these powerful technologies toward collective benefit. So the future of science isn't just about what's possible, it's also about what's right. So this is my last slide. I wanted to share this last also with you. I don't have clear answers to how we can do that, but I think it's important that all of us think of these things and engage in discussions about this. I'll finish with these references. Here are my contact details. If you're interested in working on machine learning tools, don't hesitate to reach out and apply to join my research group in the UAE. Thank you for your attention, and yeah, thank you.
Thank you very much, Dr. Salem, for this very interesting presentation. I learned a lot personally, and I'm sure the audience will benefit from your expertise and what you shared with us today. So I did receive a lot of questions. Some of them are broad, vague, some of them are technical. I'll try to do a mix of both. And just I would like to remind also the audience to not just stay on the hall in Zoom event, but come also to the Zoom links so that you can really add and ask your questions too. Okay, let me start with this first question. So this is a technical question. So you worked on GFlowNets as well as their implementation, like in Torch GFN. What are the key challenges in making them scalable and practical, and especially for domains that involve extremely large and noisy data sets?
Right, great question. Many people are trying to address these challenges of to scale GFlowNets to larger domains, and I guess the simplest answer I could give is that it's similar kind of challenges that reinforcement learning faces. So when we have large spaces, it's important to know how to explore those spaces efficiently in order not to get stuck in some local optima and miss some high reward regions. There is also there are some ways that could help solve these challenges. Maybe we can think of some hierarchical GFlowNets where we construct some meta parts of the object and then delve into the specific atomic parts one by one. We can think of maybe curriculum learning, starting from small problems and going step by step until we reach our final problem. But I would say that exploration is a big challenge, and I guess also optimization can be a big challenge here, because when we have large spaces and when we have diverse candidates in diverse trajectories, perhaps the current losses that we already have, even though that there are 5 or 6 losses that are used to train difference, are not enough, and maybe we would need to find new ones that are more efficient.
All right. Thank you for this answer. So the next question is also very quick, actually, and I would love to hear your thought about it. So it's your take on the need for huge computing power to advance AI for science, especially
Right.
when working in the global south, as in the case of Morocco, for example.
Right.
So this is, yeah.
Yeah, that's an important question. And like it's not really about global south or Morocco only. I don't know if you've seen this, but a few days ago, some researchers in Stanford University, like they mentioned that public universities or academic institutions in the US cannot keep up with the pace of big companies like OpenAI, Google, etc. So this is a question that's asked everywhere. I don't have a solution to that. I guess nobody has for now. But it's important to understand that you can always start small. An idea can always be tested on some smaller scale problems that you can even run in your own laptop, or maybe with a few $dozen of GPU credits. And if that idea you develop has some promise on some small benchmarks, on some small data sets, well, perhaps you can pitch it, write a paper about it, and you can try it in larger scale problems.
Yeah, and exactly. And sometimes, big ideas come when you have a lot of constraints, like what happened
Yeah,
with the deep
exactly.
learning field, right?
Yeah, exactly.
So, okay, so the next question, I'll come back to another technical question. It's not very detailed, but the question said, is there like a link between GFlowNets and transformers? Can we find links or not?
Okay, so an important thing to know about GFlowNets is that the network that I mentioned should not be compared to traditional architectures like multi-layer perceptrons, CNNs, RNN, transformers. But these architectures are only a component of the whole GFlowNet. So whether it's a transformer or a normal neural network like a multi-layer perceptron, this is the thing that will get trained at the end of the day. And this is like the flow predictor or the transition probability predictor or the policy. So it's like in reinforcement learning, like we have this whole environment, but at the end of the day, we learn, at least in deep reinforcement learning, we learn neural networks, whether it's transformers or other architectures that guide the agent in the process.
Okay, thank you. The next question is a long one, so please bear with me. So AI and more specifically machine learning has profoundly advanced science, and now we are witnessing AI scientists being awarded Nobel Prizes, right, in physics and chemistry, like this year. So what's your view on the future of science, and are we discarding science as formulated by Galileo and Newton, and is this good for science itself?
Yeah, this is very relevant to my talk. I touched upon a few points of this question in my talk, where we have Newton and Galileo, which were, I guess, in the second paradigm. So yeah, I do believe that there is a fundamental shift. There is a new way of doing science that we need to embrace, because actually, I don't know whether we need to embrace that or not. Like, I'm not the one to say what we should embrace. And what was the second part of the question? Or maybe the first part?
So it was actually, what's your view on the future of science? So you already answered, I think. Yeah. And
Yeah.
as we discard in science as formulated by
Yeah.
Galileo and Newton.
I don't think we are discarding that. We still have good intuitions, and there are things that machine learning can't do yet. I don't know whether machine learning can be labeled as being as creative as humans in the future, whatever creativity means. But for now, I think it's safe to argue that we still have something in us that makes us more creative than machine learning. So we shouldn't throw the baby with the bathwater.
Yeah, exactly. Yeah. So we still have a lot of questions, but I'll select just two to stay on time. So I'll come back to a technical question this time. So in this question, the question says actually DUP, is it like conformal prediction? Do you need to train again your models, or you can just use an already trained model and apply DUP on it?
There are some links with conformal predictions. So here, let me very quickly explain how it works. So you have a main predictor that's already trained. So we don't touch that. But suppose that you have some validation set that was not used to train the main predictor. So on that set, the main predictor will make some mistakes because it was not trained on that. And those mistakes, so now we'll create a new data set of inputs from the validation set and the errors that are made by the main predictor. You can think of L2 error, or you can think of the cross entropy loss, or things like that. So this creates a new input-output pairs that you use to train another neural network or another model that doesn't necessarily have to be neural net. So this second model now becomes an estimator of total uncertainty, and we can extract from it an estimator of epistemic uncertainty.
All right, thank you very much. So yeah, last question, very general again. So it's a question on AI and more specifically machine learning, yeah, playing a bigger role in science. So how do you see the difference between causality and correlation? Can AI balance these, or does it favor one over the other?
Okay, I think there are many parts to this question. Of course, like machine learning researchers, we are aware that there's a difference between causality and correlation, and traditional statistical methods, they do not distinguish between these two things, and what can appear as causality is actually just correlation sometimes. But there are ways to discover causal relationships. So I mentioned very quickly like these causal graphs, and the way to obtain the causal structure, so like the causal direction between different variables, is by doing interventions. So if you just have observational data, if you have like a data set in front of you and you analyze it with whatever methods you have, you cannot infer the causal link. However, if you intervene on that data, if you change the distribution of one of the variables and look at how it influences the other variables in your system, then there are ways to infer the causal structure. So it's a very active research area. And I do agree that it's important to distinguish causality from correlation. Like in the medical field, it's important to know what causes what disease. There's this big project called it's a collection of projects where we want the gene regulatory network, where we want to understand how different genes interact with each other in our cells in order to better understand like genetic defaults or things like that.
Yeah, thank you very much, Dr. Salem. So yeah, we can end with a nice note. Maybe if you can have some few words for the MoroccoAI community. Just the floor is yours. Just like a free note.
Could you help me like something more specific question?
As you wish, actually. If you want just to say something to, for example,
Okay.
to the Moroccans that are working in Morocco, for example, on this and trying to work on advancing AI for science. So just let you the floor. A few words.
Okay, fair.
Nothing complicated.
Well, maybe some advice for like young researchers, people in their early 20s. I guess we all have some kind of innate curiosity, and I think it's important to follow that curiosity and put ego aside for a while. And I guess believe in yourself. Like you have the skills and tools perhaps you don't have GPUs that's like OpenAI, but you have the necessary skills to provide your own ideas and test your own ideas at a certain scale. Yeah, believe in yourself and good luck.
Yeah, I agree 100% with you. Thank you a lot, Dr. Salem Lahlou. It was really interesting. I enjoyed being host for this session, and thanks to the audience for being here.
Thank you for the invitation.
And yeah, and see you for the next keynote. And thank you all.